Hello everyone! My name is Connor Smiley, and in this video, I'll be showing you a rendering framework I created at the start of 2019. My design goals weren't entirely clear when I started this, but what this turned into was a simple place for me to test different rendering techniques and different OpenGL API calls. Starting it with the most impressive demo, we have a simple ray march scene. For a more up-to-date demonstration of ray marching, check out my video titled Ray March Solar System. That one uses a current generation graphics API and the scene is much more complex. But right here we just have some simple Phong lighting on a cube and a sphere represented by, of course, sine distance functions, and we're rendering a full screen quad in OpenGL. So if we pull back the lid on this demo, the goal of this framework was to lay out code as simply as possible. I like to think of it as a C++ client for Shadertoy with a little bit more granular control if you really wish. Right here we're determining some camera direction information, and here is the CPU side of the ray marching algorithm doing some plane stuff and calculating projection, sending up all our data to the shader, and rendering the screen quad. Really nothing groundbreaking. So let's just continue on with some demos. Right here we have a batched line renderer. Let's wait for that to boot up. So yeah, again, this is really nothing impressive. I was just playing around because I wanted to try something new. I've always been rendering triangles, so I wanted to render some lines. It looks almost like some audio processing software right here. And the way I achieved this was I had a few different buffer objects. Let's take a look. Ray renderer. We had a color buffer object, and we had a vertex buffer representing height, and that was just determined with a few random numbers. So once we have all our vertex data in line, we'd simply invoke some shaders. We would populate the buffers every frame depending on random numbers, and of course send up even more uniform information. This time, of course, not rendering as a screen quad, but rendering just one draw call you can see to render a bunch of lines. So I thought that was cool because it's more efficient than rendering one line per draw call. But again, instance rendering is nothing new. The only other two demos I have in this application are some texture benchmarks. So we have a naive implementation of uploading a texture, which we can see right here. All we do is use STB to load a texture, define some parameters, like we have nearest interpolation and some clamping. We don't need a linear filter. We're just binding a single texture, selecting the corresponding shader, and we're profiling our render. Of course, this is just keeping track of time on the CPU side. What would actually matter is GPU side, and that requires a bit more effort to do accurately in OpenGL. But the important part is the difference in the logic. So in this case, we're calling text subimage 2D directly with the image data. So let's take a look at the performance here. Oh, and whoops, we're gonna want to stop our FPS logging because that will interfere with the console logs for the texture benchmark. There we go. So here we have some upside down turkey vultures by the looks of it, and we're uploading this texture at an incredible rate of what looks to be on average like just a fraction of a second. Let's go ahead. That almost seems too good to be true. I'm pretty sure that, what is it? Yeah, text subimage 2D is synchronous, but just to be safe, let's do GL flush and GL finish. Cool. Let's try that one more time. And of course, just to think out loud, Oh, okay, yeah, wow. Okay, that makes much more sense. I was gonna say there's no way we're uploading a 1080p image in like nanoseconds. So this is taking between 20 and 30 milliseconds, which is much more to be expected. So what Flush does is it ensures that all the commands in the command buffer, like on the graphics driver, are being executed, and GLFinish waits for those commands to be executed. So basically what was happening was this wasn't synchronous and we weren't getting an accurate time reading as a result. So we basically just stalled our CPU until our graphics operations were complete. Now, if we look at the accelerated texture demo, accelerated is a bit of a misnomer. What it actually does is it uses pixel buffer objects along with persistent mapped buffers. So rather than, let's see, just creating a simple texture handle, we manually define the buffer as persistent, so that way the OpenGL driver doesn't have to reallocate the memory every time, or even worse, you don't have to do some silly OpenGL driver trick to prevent it from allocating memory. Things are laid out nice and explicitly. So we map the memory once, we memcopy the result. You'll notice here that this inherits from texture demo, not necessarily the cleanest design, but given the fact that this application is extremely simple, I'll allow it. So our texture is already loaded, we just map the memory and assign our data. And now, once again, we're calling text subimage 2D, but this time with null pointer to signal to the driver that we should be fetching our data from a pixel buffer object, which is the aforementioned buffer, rather than some CPU side data directly. And again, since we're using pixel buffer objects, we have to manually sync our CPU if we want our upload to be synchronous. So let's take a look at the performance here. All right, so this still looks to be performing about 3 times worse than the naive implementation of the texture upload. Now, why would this be, even though I'm trying to optimize the memory allocation strategy and whatnot? Well, I believe the reason for this is because the OpenGL driver might be transferring twice the memory. In the naive demo, we're simply uploading the data directly, whereas in the pixel buffer demo, first our memory resides here, and then we have to transfer it to texture memory since buffer memory is not in the right format for texturing, so we might be using about twice the bandwidth. However, the advantage to this is that we can make these operations asynchronous, so if this application were to be more of a video game instead of a renderer, we can spread our texture uploads across multiple frames. And of course, right here, since this took about, what, like 30 milliseconds, I believe, or maybe it was just 3, but either way, like anything longer than like half a millisecond is completely unreasonable in a much more complex application. So it starts to become mandatory to stream our textures. That's also what this is. We have another demonstration that I won't bother running where we're basically uploading 5 textures in parallel and checking the performance, but there's nothing new in terms of implementation there. So that concludes my 5 different demos, a bit of arrays, a bit of textures. Let's take a look at the actual code. So what sort of stopped me from continuing on this framework was there was a bit too much reinventing the wheel. For something simple like testing out different rendering techniques and API calls, I wanted something bare bones. But to make something like a significant engine or a complete video game, it made much more sense to build off of existing frameworks. My favorite framework to date is The Forge. I have a couple videos on that, think super highly of that, so please check those out. But I'll just talk briefly about some design principles here. So again, in 2019, when I was a bit more new to programming, I thought singletons were cool, and when I realized I could come up with a generic singleton, I thought I had achieved the pinnacle of design patterns, when in reality I just made an overly complex global variable. And nowadays, 99% of the time, I will advocate against singletons. And even so, I use them sparingly. For example, my only two singletons are for the window and for some timing. And even then, not every portion of this application needs to know window information all the time. You can kind of just initialize the OpenGL context and forget about it. And same with the timing. It's very easy to forward delta time between inner bodies of your application. So those singletons aren't warranted, but I didn't know any better at the time. As for the screen quad, I'm pretty proud of this class. What is it? Or sorry, not the screen quad, but this class is pretty convenient, just allocating a full screen quad and simply rendering it. You don't need to keep track of vertex attribute pointers or anything. It just simplifies the draw call down to one line. What I was getting at was I'm lost in my own code base. One moment. Screen quad, it's something like vertex array, utilities, textures, rendering, array object, I believe. Yeah, this right here, so just some automatic generating and deleting of OpenGL buffers, so that serves as a base for the screen quad, and yeah, that's all I was getting at. So those are some simple OpenGL utilities, again, using STB to load images. I didn't bother with any OBJ loaders because I have no reason to turn this into a video game, but if I were to, I'd probably use something like TinyOBJ. Shaders, again, this is what I like because it gives me more flexibility than Shadertoy. I can send any data you could ever want to imagine to the shader, and we're, of course, caching our uniform locations so we don't have to re-look up the ID every time we want to communicate with our GPU. And yeah, just a relatively straightforward OpenGL shader encapsulation. And I'm using this here so we can do, I forget the term for it, but effectively chain constructors, but with methods. And that's about it. We've got some math functions, like a simple line intersection algorithm right here. I don't think I ended up using that. I've played around with a lot of linear algebra. This guy encapsulates GLM and has local and world transformations. But again, around this point is when I said, okay, there's nothing unique about this code. Let's just use someone else's framework to render. And if we need to understand some fundamentals without as much boilerplate code, let's come back here. So hope you can see the value in this. Take care.